Good day to you. You are welcome to Linear Serial Collect class. And the topic that we'll be considering for today is maximum likelihood. And we want to find the likelihood function of a Poisson distribution. So now the first thing I will write is the PDF, the probability density function of a Poisson distribution. So f of x comma theta is equals to theta raised by x exponential minus theta over x factorial. So here we have x start from 0, 1, 2 up to infinity. So now, and to obtain the likelihood function of any particular distribution, it is given as the likelihood function is given as that's L of x comma theta is equals to, we have the product I equals to 1 up to n, then we have f of x comma theta. So now in this case, our f of x comma theta, so that's the PDF of the Poisson distribution. So from here we have L of x comma theta is equals to, we have the product I equals to 1 up to n. Then the value of our f of x is theta raised power x exponential minus theta over x factorial. Now the next thing I will do here is, don't forget that I start from 1 up to n. So that means here we have theta raised power x 1 exponential minus theta over x1 factorial times we have theta raised power x2 exponential minus theta over x2 factorial. Then we'll put a triple dot in between up to, that's theta raised power xn exponential minus theta over xn factorial. So now we can actually rewrite the likelihood function of a Poisson distribution as theta. So here we have x1, x2 up to xn. So that means we can actually write it as summation x for this particular one, that's summation xi, because here we have theta raised power x1, theta raised power x2, theta raised power xn using the law of indices. So we can write this as theta raised power summation xi. So and here we have exponential minus theta. So exponential minus theta is here, exponential minus theta is here, likewise that particular place as well. That will give us exponential minus n theta. So that will give us exponential minus n theta. Then everything over. At the down part we have x1 factorial. Then the next one we have x2 factorial. Then up to xn factorial. We can write it as n xi. Then we have factorial. So since we have x1, x2 up to xn factorial, so we can actually write it as n xi factorial. So this is the likelihood function for a Poisson distribution. So now to obtain the maximum likelihood for a Poisson distribution, so the first thing we'll actually obtain the likelihood function. The next step will be, we'll now find the natural log. So we'll find the natural log. So don't forget that the likelihood function is, that's theta raised power summation xi exponential minus n theta over n xi factorial. So now the next step will now be, we'll find the lateral log. So that will be mean L into x comma theta is equals to, so we're going to have the mean of, that's theta sigma xi exponential minus n theta over n xi factorial. So we want to obtain the likelihood function, that's the first theoretical moment. So to obtain the first theoretical moment, so now we'll find the natural log of both sides. So now from this side we're going to have equals to, since we have product in between the two, that means we're going to have ln theta summation xi times the mean. So here, since we have product in between the two, this one will later change to, that's addition. So we're going to have plus the mean of exponential minus n theta over, since we have division in between, so this one will later change to negative sign, that's subtraction. According to the law of indices, that's n xi factorial. So in this case, since we have a log and this exponential, the two will cancel each other, and this sigma xi will come down. So I need to have summation xi. So this one gives us summation xi. Now we are going to have ln theta minus n theta minus ln n xi factorial. So that is what we are going to have from that particular place. So by the time So by the time you take the lateral log of the likelihood function for a Poisson distribution. So I need to have something like this. So now the next step is to differentiate both sides partially with respect to theta. So we are differentiating what we have here, that's ln of this with respect to theta. So I need to have ln this over, we have theta with respect to theta. So differentiating this with respect to theta. So this summation xi will remain as a constant. We can apply dot through over here. So this one give us summation xi in brackets. So when you differentiate ln theta or log theta, that will give us 1 over theta, because when you differentiate this theta, that will give us 1 over that theta that you differentiated. So now here we have minus n theta. So differentiating minus n theta with respect to theta, that will give us minus n. So now differentiating minus ln n xi factorial with respect to theta. So there is no theta in this case. So we'll take that one as a constant, that will be 0. Then we equate everything to be 0. So after finding the natural log, we equate it to be 0. So that means from here we are going to have summation xi over theta minus n equals to 0. So similarly, we can also rewrite it as summation xi over theta equals to n. So from here we can cross multiply. So by the time you cross multiply from here, we are going to have that will be n theta equals to summation xi. So now that means from here the value of theta is equals to summation xi over n, which is same thing as what? X bar. So we have theta cap equals to summation xi over n equals to x bar. Thank you so much. Kindly like, subscribe and share, and follow for more.